So last class we discussed the introductory part, complex power. Okay. So in the introduction part, what we discussed? We discussed that power system is an integral part of the modern society, and without power system, without electricity, nothing can go on smoothly. So we completely different picture. In fact, the AI-based methods or all the data centers, they use power, they require power. Okay. So without a proper power system, even AI servers, they will also struggle. Okay. Okay. And also we discussed that the core of power system is to transfer the complex power P plus J, where P stands for active power, Q stands for reactive power. Okay. Active power is the one that we require for various equipments to operate, whereas reactive power is as such not consumed, but nevertheless is required for operation of the power system. Okay. Without reactive power, there is no conversion between mechanical to electrical and oil. Okay. So now we will move to the next part, which is transmission capacity. Okay. So these two are explicitly mentioned in your syllabus, but these are part of EPTV. Means you can say power generation, transmission, distribution. So in power transmission part, you should have read about this complex power as well as transmission capacity. This is the next 6 classes that we will discuss are actually the PSOC, the power flow part. Now someone tell me what you understand by transmission capacity. What is meant by transmission capacity? Anyone? Maximum power? Maximum power that can be transferred through a transmission line. But when we say maximum power, what exactly is meant by maximum power?
Power that can be transferred with maximum efficiency.
Just like human beings. So you have a maximum capacity to do some work, but then you have a lower capacity to do the work without affecting your health. If you do the maximum capacity work, then you might end up affecting your health. A permanent damage may also do that. But that is your maximum capacity, you can do that. But again, there is some kind of capacity that you can always do without harming yourself. So similarly, the power system has two kinds of transmission capacity. One is known as stability limit. Okay. The other one is known as the thermal limit. Thermal limit and stability limit. So if you work too hard, you may damage your health irreparably. It may be irreversible. So similar thing is thermal limit for a transmission. So when there is a thermal limit, the transmission thermal limit means what? Thermal limit means whenever power transfer occurs, I square R losses occur in the transmission line. Because of the I square R losses, heat is generated. So because of the heat, the transmission lines may expand. So they may permanently sag. Okay. Burning out transmission line is a very remote possibility, but before that, sagging, permanent sag will occur. So when sag occurs, the transmission lines may touch some object which is below it. Okay, leading to a fault. Okay. So we don't want to go to the thermal limit. It's a maximum capacity. The transmission line, we don't reach that. Okay. We are mostly concerned about the stability limit. Okay. Stability limit is the power that the transmission line can transfer without affecting the stability of the power system, and you know it. There is a formula for it. This is related to the synchronous generators power generation. Okay, what is the formula? Power angle equation. From the power angle equation, it is obtained. What is that called? What is the power angle equation? Yes, very good. Power angle equation is EV by X sin delta. Okay. So for a transmission line, it will be V1 V2 by X sin delta. So delta can be at most 90 degree. So in that case, the transmission capacity of a transmission line is simply V1 V2 by X. So if you want to increase the capacity of the transmission line, you have to reduce the reactance. Just like human beings. If you want to increase your capacity, don't react too much to various things. If you react too much, if you emotionally react, then your capacity to handle the problem will decrease. Similar with the transmission line. If you decrease the reactance, you can transfer more power. If you decrease your reaction, you can do more, your performance will be more. Okay, similar concept. So we'll go to the details. So mostly we are going to discuss these two limits. Okay, transmission capacity. Okay, so when we say power system, we are mostly concerned about a three-phase system. Why? Why we prefer three-phase, not single phase? One is more generation occurs with the same amount of conductors. Next, other one. Three-phase transmission distribution in the final one. What is the advantage? Other one is losses will be less. Okay. Three-phase transmission is more efficient. Okay. Over long distances. There is a limit beyond which DC transmission is more preferable. Right? What is that limit called? There is 65 kV is the high voltage. Okay. But there is a distance beyond which DC is preferable. Okay. Find out. Okay, there is a term for it.
300.
Okay. No?
300.
300 is more than that. Okay. It's more than that. But here we are concerned about normal transmission distribution. Three phase is more preferable because it is more efficient. Okay. Therefore, we have developed three phase generator. Three phase generation is more efficient. If you generate three phase, you must transmit three phase. Right? So, what is the difference between a three phase system and a single phase system? Okay. So that we see here. So in a three phase system, there are three voltage waves which are 120 degree apart in phase. 120 degree apart in phase. 120 degree apart in phase. Okay. Okay. The corresponding phasors can be written as, you can write these phasors. The phasors for three phase generation are 0 degree, minus 120 degree, minus 340 degree. So the three generator terminals, they will generate three phase voltages which are 120 degree apart in phase. Write it down. Only this one. Okay. And the line voltages are simply VAB means VA minus VB, VC means VB minus VC, VCA means VC minus VB. Okay. So if you do the vector addition, you will find out that the line voltage is √3 times the phase voltage. So if you find out, you will find out that the line voltage is √3 times the phase voltage. So whenever you see the insulators in the transmission lines, it is designed for line voltage. Okay, it is designed for number of discs in the insulators will depend on the line voltage, rated line voltage. Okay, so these two, what highlight that you write. So this is three phase. And this is the whole transmission system shown as a network. Okay, this is the whole power system shown as a very simplified network. Okay, so what is this? So as you can see here, you have a three phase generator. So we are concerned about both only alternators here. So PV, wind, all this kind of generation do not come into picture. These are mostly two kinds of generators. What are those? Conventional power system, what are the generators? Okay, you can have only two kinds of generators. One is cylindrical, one is electro. Okay, or we say turbo, that is for steam and nuclear generators, and this is for hydro. Okay. Hydro capacity has been percentage. It is very less now, below 11%. And mostly we have coal-fired thermal generators, and they are all steam engines. Even nuclear power plants also have three-phase synchronous generators. So all these three-phase synchronous generators generate three-phase voltages. What are three-phase voltages? These are just simply three different conductors. Okay. So three different conductors which are 120 degree apart in space. 120 degree apart in space. They generate three-phase voltages which are 120 degree apart in phase. Okay. Three conductors 120 degree apart in space generate three-phase voltages which are 120 degree apart in phase. Okay. So now that you have got three-phase voltages, that means there are three wires that are coming out of your generator. You need three transmission lines. So you have got three different transmission lines which are going to the load. Okay, which are going to the three-phase load. So this is our transmission system. This is the transmission system. The return path is the ground. The return path is the ground. So you know, by very nature, the fundamental of electrical charge says that you need a return path. Otherwise, there will be any current. That is the very basic of electrical engineering. No questions are. Okay, the basic of electrical. That is the nature of the charge. Charge is the fundamental quantity. Charge. What are the fundamental quantities of nature? 7 or 5. How many fundamental quantities? 7 quantities. Current is not fundamental quantity. It's charge. Okay. Luminous flux. Charge. Then mass. Okay. Find out. Similarly, charge is the fundamental quantity. For charge to flow, there must be some return path. Hello? Okay. Now, what is the content of transmission and distribution subject? So you discuss about what are the various transmission lines, how they are designed, what are the various insulators that you discuss, and what are the various power plants that also embedded in one module in power generation, transmission and distribution. In power system operation and control, we will see the nature of this. How this can provide electricity continuously without any disturbance, and if disturbance occurs, how to handle it. So that is the content of PSOC. Correct? Okay. So in three phase, in single phase we have seen it is VI. We have found out. Okay. Power is equal to VI cos phi plus JPI sin phi. Active power, reactive power. So how it transforms to three phase. Okay. So considering impedance Z, okay, having an angle maybe phi. So the current lags behind the voltage by angle phi in various stages. This is the power factor angle. This is known as the, those who are not following the basics, this is known as the power factor angle. Okay. The corresponding phasors are IP minus phi, IP minus phi plus 120, IP minus phi plus 240. These you write these phasors. The current phasors for a three-phase system are, the current phasors for a three-phase system are, the current phasors for a three-phase system are, okay, the current phasors for a three-phase system are, so first you wrote the voltage phasors, now you wrote the current phasors. Okay, point number 1, point number 2. Point number 3. Power in a three-phase circuit is given by, many of you make silly mistakes here. Power in a three-phase circuit is given by, okay, 3 into Vp IP cos phi, or you can write this as root 3 into VL IL cos phi. Okay. So whenever you find out current for a particular MVA capacity, do not forget to keep the root 3 if it is a line voltage. If it is a line voltage, do not forget to keep the root 2 part. Okay, white fault calculation. In module 4 we will see this in detail. So this is the problem that I asked you to solve yesterday regarding induction motor. Okay, question number 2. this question is, question number 1 is very straightforward in the first PPT is there. So what is the question? How to solve it? The equivalent induction motor load on a section of 138 kV transmission network. So this is the voltage, three-phase voltage. This is three-phase line voltage. Can be represented by the equal impedances of this. Okay. Find phase currents, real and reactive power demand. So first thing that you have to do is convert this into line voltage. These are all generators are connected in star. All synchronous generators are connected in star because it is easier to take the terminals out. Induction motors are connected in delta, but induction generators are connected in star. Okay. So you take 138 by root 3, then divide by J to find out the current. Then you find VI cos phi real power, VI sin phi reactive power. Okay. Same thing. See, first all of you see here. First you have to convert to phase voltage. Okay. Then the current, phase voltage divided by impedance, the current. Then you find out the power factor angle and then real and reactive power. Okay. And this is the total apparent power. This is the very basic problem which is at the base of PSOC. So if you do not understand this problem, you cannot solve digital problems of PSOC. Okay. So solve it. Next. So this one I discussed at the beginning. So for a transmission line, there are two kinds of limit. One is known as the thermal limit, the other one is known as the stability limit. Note the term static there. We are concerned about the static stability limit. For example, human beings have two kinds of limits. One that we can tolerate when we are in a good mood. The other one is when we are in a difficult situation, how much stress we can handle. Just like in a competitive exam. How much stress you can handle in a normal university exam, how much stress you can handle in a competitive exam. So we see that our capability changes. Our capability changes based on the situation. Okay. Sometimes we are more capable, just like a sports person. He can travel, he can run at a very high speed, which is normally impossible for a human being. They can do that. So under dynamic situations, our capability changes. Same for the synchronous generator. Okay. So whenever a fault occurs, a synchronous generator power angle goes beyond 90, and we have read in theory that 90 is the maximum limit. Delta is equal to 90 is the maximum limit. But a synchronous generator can go beyond 90 during a fault, but for a very fraction of a second. Okay. So here we are concerned about only the static stability limit. That means which is what is static stability limit? Delta equals to 90 degree. Delta 90 sin delta 1, and for operational purposes we keep it at 30 degree. In your power angle experiment in the machine to lab, the angle you have got not more than 20 or 15 degrees in the lab. So the static transmission capacity is defined under conditions of slowly increasing load. Okay. So what is the static capacity of a transmission system? When the load changes, normal day-to-day load changes, can it handle? Okay. So it's just like you. So normal day-to-day attending classes, going to the hostel, having food, in between going somewhere, coming out, can you handle this stress? If you can, then you are static stable. Okay. However, during campus interview, during exams, okay, that will be dynamic situation. Okay. This is day-to-day. The phase resistance R, see, R is very less compared to X for a transmission line. Okay, R is very less compared to X. We want our line to be very much inductive so that losses will be less. Okay, but still every conductor has some R. So because of this R, there will be some ohmic loss. Okay, the conductor temperature rises until the heat dissipation rate is in balance with the heat loss. See, long before the conductor melts, other permanent damages that is non-reversible sag occurs. Conductors never melt, it is very rare, but sag will be there, it will expand. Okay. The thermal stability limit determines this you write, this one you write. The thermal stability limit, thermal capacity limit determines the maximum power transfer on relatively short lines and underground cables. Okay, maximum power transfer. Short lines and underground cables we consider thermal limit. Okay. For longer lines, The phase impedance sets the current and power limit before the thermal capacity is reached. That means stability limit is reached before the thermal limit reaches. Okay, for longer time. So we are not bothered about the thermal limit for longer times. Okay. Write it, thermal limit.
Sir, will sag not occur in short lines?
Yes, it will occur.
Why do we not consider that? Like, because again, if it's also heating, that
Yes, but we don't reach the thermal limit. Okay. We say maybe 40%, 50% of the thermal limit we keep as a design limit. Okay. Now we are not bothered about that in longer lines because the stability limit will reach first. But in case of a shorter line, the stability limit and thermal limit may be near to each other. Okay. Okay. So what is our objective now? See, our objective for this whole class is to determine the transmission capacity. So now we know there are two kinds of capacities: thermal limit and stability limit. Okay. The next thermal limit now you know, that is I square R. I square R is the thermal limit. So what is static limit? Static stability limit? It can be evaluated under various conditions. Okay. So you just write these conditions and we will just write the answers. There is a derivation here which is taken from Elder 2. It is not required for it. It is only for your reference. We just need to know the actual final values. Okay. So under what conditions you will see this? Okay. The first thing is sending end voltage is maintained at constant level. Okay. Receiving end voltage is uncontrolled. See here. Real power load at the receiving end is slowly increased. Reactive power loads Q2 is set to 0. These three things we will see: case 1, case 2. So write down case 1, V2 is uncontrolled. Just write case 1, V2 is uncontrolled. V2 means the receiving end voltage. Case 1, the V2 is uncontrolled, the receiving end voltage. Okay, case 1, the receiving end voltage is uncontrolled. It can vary. So what is the limit there? So this is a simple derivation. So here we will, the answer is this. Just write down this. So this is the limit. The derivation is given before, it's not required. Only write this result. Okay. So this is the transmission capacity when V2 is allowed to vary. But VT is generally not allowed to vary. Right? We cannot vary the load voltage. It will affect the load performance. Okay. This is only a theoretical case where the voltage V2 is allowed to vary. Let me know the problem. Do you write? Okay. Next, case 2. So case 1 answer is this. Case 2. Voltage V2 remains constant. Case 2. Voltage V2 remains constant. Which is an ideal case because we always want that the receiving end voltage remains constant. Otherwise that will affect the loads. So here what are the various things? The tip of the voltage phasor V2 must move along a circle having a radius equal to the specified voltage level. For derivation, the reactive power in a controlled fashion either be injected into from bus 2 or meet the higher voltage requirement. Reactive power is injected. See, whenever you allow the voltage to vary, you are not bothered about the reactive power. But if you want to keep the voltage constant, reactive power must be supplied. So just like wind farms. Suppose a wind farm is connected there as part of a distribution system. You know that wind farms use induction generators. They have no source of reactive power, so they take reactive power from the grid itself. So that will reduce the voltage. Therefore, we need some reactive support for the induction generators. Similarly, to maintain the voltage, we need reactive power support. Okay. So in this case, the answer is this. Write down. So in the case 2, this is the formula that we discussed at the beginning. So this is actually the under normal condition, the static stability limit or the transmission capacity. Okay. V1, V2 by X and delta. And the reactive power at sending and the receiving end are given by these two formulas. Okay. Which depends on the voltage, which also depends on the voltage. So Q1, Q2 means reactive power at the receiving end. Q1 means reactive power at the sending end. Okay. But this is not transmission capacity. This is the transmission capacity. So this is the transmission capacity. And to achieve this capacity, to keep the voltage fixed, we must have these two equivalent. So in case of a flat voltage profile, an average reactive power can be obtained, which is given by this. So these three formulas you write. Okay, two cases we have considered. Case one, when voltage was allowed to vary, which is not a practical case. Voltage is never allowed to vary. The other one is when voltage remains constant. So that is a normal situation under which you have now concluded that the transmission capacity or the static stability limit of a transmission line is given by the formula V1 V2 by X sin delta megawatt per phase. Per phase. It is a per phase one. Okay, single phase. We have when we can extend the single phase results to a three phase system. Under what condition? Under what condition can we extend the results obtained from a single phase analysis to a three phase system? Under balanced load. Under balanced condition, we can do a single phase analysis and simply multiply 3 to get the three phase equivalent. Okay. So if it is the transmission capacity per phase, then and if it is a balanced system, you simply multiply by 3 to get the power for a three phase system. Okay. Okay. So what are the conclusions from this? So these are some questions that may be asked in the gate examination in some form. The real power reaches its maximum, the static transmission capacity at delta equals to 90. That is the maximum limit under steady state. Under steady state, always remember, delta can go beyond 90 under transient conditions, fault conditions. Okay. The transmission capacity increases as the square of the voltage level. So this is the reason why we prefer high voltage transmission. The more you increase the voltage, the more is your transmission capacity. Okay, that's why we prefer. What is the current transmission level? 132 kV starts from 132 kV, 500 kV, 765 kV, and so on. And beyond a certain voltage level, as someone said, it is DC. Okay. The direction of the megawatt flow is determined by sin delta. Positive delta V1 leading V2 results in megawatt flow in the direction of 1 to 2. So voltage level is not deciding the direction of the power flow, it is the load angle. Voltage angle or the load angle. Load angle is again directly related to the what? The prime mover. What is the difference or what is the phase difference or relative position of the prime mover who is rotating with respect to the rotating magnetic field? That is delta. So it eventually depends on the prime mover, the real power input. Delta depends on the real power input and therefore the power flow in the transmission line is dependent on the difference of the voltage angles, not voltage magnitude. Always remember, voltage is important to maintain a steady profile so that power flow can happen. Voltage collapse not occur, but actual power flow can occur only when delta difference is there. Okay. Pass voltage magnitude do not determine the megawatt flow direction. Okay, you cannot increase the voltage and you do not expect to increase the power flow. Real power is same at the both ends. Reactive power are different. Same under real power is same at both ends under the assumption of no loss. Whatever you transmit, you receive that, provided there is no loss. Okay. If V1 greater than V2, megawatt flow is in the direction of 1 to 2 and vice versa. So voltage is rated higher than actually the reactive power flow happens, not the real power. We may define the average reactive power flow in a line to be right now. This is the average reactive power flow in a line. This last line you write, it is V1 plus V2 by 2 square, V1 square minus V2 square by 2x. Okay, this is the average reactive power flow in a line. Okay, done. Okay, now rest of the class we are going to solve this question number 3, 4 and 5.